So in the last lecture, I was dealing with half-range functions, and actually we converted to any interval length. You may remember that the whole program started off with us working with pi, minus pi to plus pi as the interval length. And that's useful because we're dealing with cosine and sine functions, big functions that are periodic over 2 pi. So then it makes sense to start off working in the interval length of 2 pi. But I showed you in the last lecture that actually you can work with any length you like. It can be minus 5 to plus 5, minus 7 to plus 7. Or if you want, you can, just like in the pi world, you can go from 0 to 2 pi. The function is still periodic in 0 to 2 pi. In fact, the sine and cosine functions are periodic between a and a plus 2 pi. You understand that? You can start at any number, like 0.5. And then if you have 0.5 plus 2 pi away, that piece of curve, which is part of a sine wave, will repeat itself. So the period is 2 pi. In other words, you can start anyway, as long as you maintain a length of 2 pi. You're okay. So you can go from 0 to 2 pi. Likewise, now I said that you can actually convert to any number whatsoever. So you can write a Fourier series f of x for f of x as sigma a sum of ak cos. All you have to do is change kx to k pi x over L, and then the periodicity is preserved. Except that the interval, the period is no more 2 pi, it'll be scaled by pi over L, which I proved yesterday. So it'll be k cos k pi x over L plus bk sine k pi x over L. And then the AK and the BK have the very same meanings that they had previously. The AK, the A naught will be 1 over 2L, integral from minus L to plus L f dx. The AK will be 1 over L, integral minus L to L, f cos k pi x over L dx. And the BK likewise will be 1 over L, integral minus L to L, f sine k pi x over L dx. So those are the versions now of any interval length. It behaves the same way. Now, if you're dealing with odd and even functions, like if the function f is odd, then only the cosine part will survive. It will be, sorry, did I say odd? If it's odd, then the sine part will survive. Because odd times odd will be even. And then you'll get 2 over L. In other words, you don't have to go from minus L to L. You can if you want, but if you want to shorten your work, you can make this 2 over L, 0 to L, f sine k pi x over L. So that will survive there. If the function f is even, on the other hand, then only the cosine part will survive. So you will have even times even, which is even, in which case the result is even here. Then it allows you to write this as 2 over L, 0 to L. Just as we've done before. So that works in the same way. Then we dealt with half range. So you see, when you're given the interval length, let's say you are given the interval length 0, 50. Now you don't know, is that half range or full range? Well, the question will tell you that this function is periodic in the interval over a period of 50. Then you know every 50 units it will repeat itself. Alternatively, if it doesn't say that, then this must be taken to be half range. In which case, you've got to then add the even extension on the left or the odd extension on the right to create a fictitious function. However, that fictitious function works because indeed that answer you get will converge to the piece that you want. You will get a free piece on the left, but it's irrelevant. You can discard it. The goal there is to find the Fourier series for some piece of function that we give you. If you get some extra bits, well, okay, it's fine, but you don't have to worry about it. All right, so I was working with one example now which shows you all three scenarios. So let's quickly go over that again. This example here is quite a good teaching example. It was example 15, where you were given the function f of x equals x, and you were told that x lies between 0 and 10. The question was to find, firstly, the Fourier series, secondly, the Fourier cos series, and thirdly, the Fourier sine series. These three scenarios are considered, they are being required. So it's actually told you what you must produce. These are the most useful ones. Now, if we tackle the Fourier series by itself first, if we're dealing with the Fourier series, then that length 0 to 10 is actually 2 times the length. 2L is 10, in which case L is 5. So that's the first thing to realize. 2L is 10, in which case 1L is 5, and so because x is odd also, you will find that odd. So the shape. Let me draw the shape here. Let's see what it is that will be repeating itself. So from 0 to 10, that's a function y equals to x, and that's a full range function because I want the Fourier series. It didn't say Fourier sine or Fourier cosine, so you have to interpret that to mean a full range series. So if you work out a naught 1 over 2L, so in this case 1 over 10. I think we did this part, right, in class. 1 over 10. I'll just put it in here for completeness. Integral from 0 to 10 of x dx, and you work that out, you'll get 5. And because it's odd, you know ak will be 0 finally. And then bk, you work this out, it will be 1 over L, which is 1/5, integral 0 to 10 x sine k pi x over 5 dx. And if you work this out with integration by parts, eventually you get minus 10 over k pi. Now, that's okay. I think you can do that calculation by integration by parts. You have to be very careful, but it's something that you can easily do since you're quite good at this. The question is, what does the graph look like? And how do the next two graphs differ? Well, the graph here now, every 10 units, 10 is a full range. So 10, 20, 30, you're going to have the same shape repeating itself, cut and paste. Even on the left, so the function y equals to x, that piece will just keep repeating itself. That's what that Fourier series will generate. This Fourier series, if you write it in full, these are the coefficients, will generate the shape here. Periodism. Periodic. That's why when I use the word cut and paste, I'm quite well informed. It actually it allows you to continue a picture. That's why it's so useful in image processing. If you look under the bonnet of most image processors, they are Fourier series. Now, let's contrast this whole thing with the Fourier cosine series. So this time it's f of x equals to x, and x belongs to 0 to 10. Okay, this time the length is 10. So from this we can gather that 2L is 20. Obviously, since it's a Fourier series, there will be no sine part, so Fourier cosine. So A naught will be equal to 1 over 2L. Yes? Say again? Yeah. Yeah, because that was 0 to 10. The function is defined only there. You have to work only where the function is defined. 0 to 0 to L. Hang on. We are defined from 0 to L. A naught is 1 over 2L, integral from 0 to. No, no. It'll actually be 2L, 0 to 2L, because you see, like when you have a 0 to 2 pi, if you have minus 5 to plus 5, then the integral is from minus 5 to plus 5 in the easy. When I take it to 0 to 2 pi, the interval is 0 to 2 pi. Here it should be 2L. That's the mistake. This part here, the formula should have A naught is 0 to 2L. Thanks for correcting that. That's right. This will be 2L. Well, here I got minus L to L, right? I'm covered there. Because this problem has got 0 to some number. If it was from minus 5 to plus 5, it will be 10. Minus 10 to plus 10, it will be 20. So I'm actually using 2L here. I'm actually using 2L here. It's 10 here. Any other questions that are not clear to you? It's good to ask clarifying questions like that, so that you can make it clear in your head and you won't be wondering about it. So this one here is 1 over 2L, so L. Oh, I can actually use here, it's like half range. Remember, with half range, you can double. So 1 over 2L can become 1 over L. So it can become 1 over 10, integral from 0 to 10, because I'm doubling. Actually, so it's actually 1 over 20, integral from minus 10 to plus 10. Why is that? Because here, when I'm finding the Fourier cosine series, remember I said you have to add on the negative piece here, the even extension. So the part that will be repeating itself is this V shape. This is half the function. To invoke the Fourier methods, I must have a full function. So I got to create this tail here, which I said is like a fake thing. Then this entire thing now will start to repeat itself. Like this. Okay, so this here will be 20, 30, 40, and so on. Minus 20. So this shape here will have a length of this shape here. V shape. It has an integral length of 20. That's the full length as well. 2L. And that shape repeats itself basically here. From here to 50, 50 to 50. From minus 20 to minus 30. You get this part. In the exams and tests, we ask you to draw the pictures also. So it's going to be 1/20th of minus 10 to 10, but because we know it's even, we can reduce this to 1/10 integral 0 to 10 x cos k pi x over 10 dx. 10 dx. K pi x over 10 dx. Not 5, 10. And so this answer turns out to be 0. I'll just quote it from what I have here. 0 if k equals even, and it's equal to, what's the answer? Minus 40 over k squared pi squared. if k is odd. You know how this k squared and so on appear? When you do the integration by parts, you know the second integral, you have a 1 over k pi, and then you integrate cos k pi, and you integrate sin k pi, or whatever it is. There'll be another k pi. K squared plus k. Well, you know, I'll finish it, you know. This is AK. This is AK, so. This answer here turns out to be 5. Sorry, I think we did this one in last week's work. We were left with the sine part. All right, let's now do the sine. Just to end this part of the Fourier sine. It's a nice example to show you how all three work. So if you have any confusion, you can clarify it right now in this example. Again, this time we got f of x equals to x, and x belongs to not 10. That, because we're dealing with Fourier sine, it's like a half interval. So again, the length is 10. Twice the length will be 20. And it's odd. So the sine part, of course, will be the surviving part. We will get bk equals to 2 over 10 integral 0 to 10 x sine k pi x over 10 dx. Okay, and then if you finish this off, I forgot what the answer. I didn't actually work this out. I didn't even look in the book, but I think the answer is minus 40 over k pi. It'll be the same answer as the one above. Let's see. Minus 10 over k pi, yeah, but I think here there'll be a 40. There'll be a 4 that appears here. And this is for all k. The symbol means for all k. For all k. Okay, now what does a graph look like? Do you think you can draw a graph? What is it that repeats? Do you think you can draw it on your page? This Fourier series that I calculate here, what will it converge to? What graph does it converge to? Well, what is given is 0 to 10, y equals x. To draw the Fourier sine, or to invoke the Fourier sine series, what part must I add on to build it up? And as you can see here above, in the Fourier cosine, I have to add on this even extension. What do I add on here in the case of Fourier sine? Yes, I must add in the odd tail here, right? The odd extension here, which will be in this quadrant here. Minus 10 up to plus 10. So that's the full shape now. So now 10, 20, 30. That is the shape that will keep repeating. Okay, so minus 10, minus 20, minus 30. So this shape here will continue to infinity. But can you see the differences between the three? But in all three cases, I could obtain this Fourier series for this piece here. That's all I wanted to get. That's all I want. I wanted to find a series that represents this thing here. So if I choose a cosine version, I'll get the extra V shapes. If I choose a sine version, I'll get these extra tails here. If I work the full Fourier series, I'll still get the same thing repeating itself. Either way, I get a function or a series which converges to the relevant function in the right interval. Any questions here? That actually conveys that whole meaning of what we are doing so far. We are trying to write a function in the form of a series of cosine and sine terms. We started off working with minus pi to plus pi. There, the coefficients were something AK and BK. The AK was an integral of f cos kx and f sine kx. Then I said we can change the interval to anything. Then it becomes cos k pi x over L, sine k pi x over L. That's all we've done for the last 8 lectures, I think. So if you can understand that, the rest of it is actually you doing donkey work, carrying out the integration by parts. That part is not for me to do. That part is for you to do, where you sweat it out and get the right answer. That's why I told you in the tuts. If you get it wrong the first time, don't scream and throw your toys out of the cot and all that. Do it again and again until you get it. Because you will be making some mistakes with the sign. You see, I make some mistakes while working. It happens. There's so many things going on in the problem, especially with the minus signs. It's hard to keep a track. All right, so let's now bridge on to something slightly different. Same thing, but now in a new garb, as it were. It will be the complex form of the Fourier series. Complex form of the Fourier series. Okay, remember, this course is a course in complex analysis. The Fourier series is most useful when we have complex functions and so on involved. And life is not the same as when they are real valued functions. Things can become quite different and difficult. We need new specialized mathematical techniques, like Cauchy's integral theorem and stuff. The integral is not what you think it is. In fact, what the graph looks like is not what you think it is. So you'll be quite surprised, and it's quite, they say Cauchy's integral theorem, which is the highlight of this course, is one of the most beautiful pieces of mathematics ever discovered. And you'll see when you come to it why that is the case. Let's recall a few things that you have learned in previous years. Recall. How do you write cos x and sin x in terms of exponential functions? How do you write it in terms of e to the x, e to the I x, and stuff like that? Yes? Okay, let me start off with a more familiar problem then. Every year, everyone forgets this here, so I have to start off with something. You have come across Euler's theorem. E to the I theta equals to cos theta plus I sine theta. Does that ring a bell? Okay, let's just stop there. E to the I theta is cos theta plus I sine theta. If I change to e to the minus I theta, I can get cos theta minus I sine theta. Okay, that's Euler's theorem. Euler, the famous Leonhard Euler, who went blind when he was about 28 years old. And then when he was in his mid-30s, his house burned down with all his mathematical works in it, including his second theory of lunar motion. By this time, when he was in his about 38 or so, he became totally blind. And then how will he get back all his work? His house is burned down with all his mathematical works. He sat and re-derived all his results by memory, from his memory, and published his second theory of lunar motion, the motion of the moon. That's very complicated, right? Remember the moon moving around the earth. The earth is spinning around. And then the earth is also moving around the sun. Now you've got to mathematically model the movement of the earth, the locus of the moon, in space-time. That's a very hard problem. Euler is one of the great legends of mathematics, amongst the big heavyweights, with Gauss and Sir Isaac Newton and others. Really the genius of that era. Okay, so now, using this result here, I can use simultaneous equations, equation 1, equation 2. I expect you to have done this in first year, but I'm just recapping it because you may have forgotten. If I subtract equation 1 minus equation 2, I can get a formula for cos theta. Cos theta is equal to e to the I theta. Well, let me add that first to get cos, so that these two kill each other. I add them up. Now I get 2 cos theta here, divide both sides by 2. So it'll be e to the I theta plus e to the minus I theta over 2 is equal to cos theta. Well, I got that already. Likewise, if I subtract equation 1 from equation 2, or the other way around, I can get sine theta equals e to the I theta minus e to the minus I theta upon 2i. See these i's here? There'll be 2 of them. They will finish up underneath the division sign here, as I've written here. So that's the formulas for cos theta and sine theta. So in our language now, cos kx is e to the I kx plus e to the minus I kx over 2. Sine kx is e to the I kx minus e to the minus I kx upon 2i. Or you'll also remember from Euler's theorem, e to the I theta equals to cos theta plus I sine theta. If you put in theta equals pi, you'll get e to the I theta equals to cos pi, e to the I pi, cos pi plus I sine pi. And we know the cos pi is -1. Sine pi is 0. Therefore, you get e to the I pi plus 1 equal to 0. This magnificent formula here is one of the most enigmatic formulas in all of mathematics. You've seen it before, right? The first e to the I pi plus 1 equals 0. What's so amazing about this thing? There are 3 big boys in mathematics. Excuse the gender bias. 3 major heavyweight numbers in mathematics. Which are they? Which are the 1, 2, 3, 4, 3 special numbers in mathematics. E is one of them, which is the natural logarithm. It's a base which nature works in. In high school, you work in base 10, but you soon realize life doesn't actually work that way. In university, you're introduced to E. And you find there's an integral, and so on, blah, blah, blah. The other one is pi. Where does pi come from? Where did it come from in your life? Where do you see it first? Primary school, you learned about the circle. What is the definition of pi in primary school? You are studying a max you. Shall I put the recording off? Or we go to this grilling where you feel a bit ashamed now. You forgot what you don't know what pi is. Pi is the ratio of the circumference to the diameter of any circle. You take any circle, anything that's lying outside, measure the circumference, measure the diameter, take a calculator and divide the two, you'll get an answer 3,141592. Those are infinity. The transcendental number. Transcendental number means you can't draw it. We said this in the first section. Unlike the irrational number like root 2, which you can't draw. Hypotenuse of a 1 by 1 square is root 2. A number like pi you cannot draw. You can't use ruler and straight edge and compass to construct a number like pi. There are 3 cornerstone problems in ancient mathematics, and that's one of them, whether you can construct pi. Answer is no. It's the same for E, by the way. You can't construct E. It's a transcendental number. Then what is the third heavyweight number that's in that formula? Which in high school you may have thought is totally useless, but now you realize it's a game changer. Which number is that? There's only 3 I can see here anyway, right? There's E, there's pi, and pi. Those 3 numbers, pi comes from the square root of -1. Complex numbers. They come from 3 different worlds, right? E comes from logarithms, natural world, I comes from complex numbers, pi comes from geometry, basically. They appear in all those integrals we calculate, area of a circle and stuff in first year. So yet all 3 numbers now are lumped up in the same formula. Who would have thought that these 3 guys actually belong to the same family? They are intrinsically linked together. This time you applaud. Obviously, it turns out, inspired by this major result. Many conventions of mathematicians, conferences and stuff, you'll find the t-shirt you have that logo. It's a common logo for conference t-shirts. The pi I plus 1 equal to 0. Of course, the other number 1 is an important number. You might yawn at the number 1, but it's a multiplicative inverse in algebra. Number 0 is also it's an identity element in algebra. So these are major numbers innocently appearing in one formula, which that's why some people say this is called a godly formula. There's no good reason why they should all be linked together, but they are. And that's the rhythm and the melody of mathematics. It's really a beautiful field of study that you're getting into here. Okay, so what I wanted to say here was that yes, e to the pi I is equal, where am I right? Is equal to minus 1. So e to the I k pi is minus 1 to the k. Came across that guy before in our game. Yeah, we have, right? This was the same as cos k pi. Or cos of minus k pi. On the tuts, on Monday, some people didn't realize that cos of minus k pi and cos of k pi are the same thing, and they equal to minus 1 to the k. And then you can start to talk about odd and even if you want. You only start to talk about odd and even if there's minus 1 to the k minus 1. Because in one case it will be 0, in the other case it will be minus 2. You don't always talk about odd and even. What else? Yes, okay. The other thing I wanted to point out before I plunge into the work is 1 over I. How can you simplify 1 over I? What's, okay, if you multiply the top and bottom by I, you'll get I over I squared. What's I squared? Huh? Minus 1, so you'll get minus I. So keep in mind that 1 over I is minus I. You're going to need all this kind of stuff when you do the calculations. Believe me, it's going to get much harder than it's been already. You may have been swearing at the integration by parts being done twice and stuff like that, but your life is not going to get any easier. It gets worse, as you know in mathematics. All right, now, I'm now going to derive the complex Fourier series. So now I'm going to derive the complex form of Fourier series. And this is quite beautiful also at the end because it turns out there's only one component to work out here. But for me to prove that, it'll take me a bit of time and some effort here to convince you that it works that way. But let's go. Let's see if we can do it together. So let's start off with the familiar terrain. F of x is sigma ak cos kx plus bk sine kx. We'll do this problem for minus pi to plus pi, and later on we'll say we'll make the transformation to minus L to plus L by just changing x into pi x over L. Okay, so now must I go cos kx? I won't write the limits yet, just to save space. That's ak cos kx is e to the I kx plus e to the minus I kx over 2 plus bk sine kx is e to the I kx minus e to the minus I kx over 2i. Let me just take out the half as a common factor there. And then let me multiply out. Let me multiply out the brackets. ak e to the I kx. ak e to the I kx plus ak e to the minus I kx plus bk e to the I kx minus bk e to the minus I kx. Next, I will group stuff. Group these e to the I kx's. And group these other guys here. Yellow guys and the green guys. Let me get another color. we group these yellows and the greens. Rearrange them. Nothing funny going on here. It's just the standard calculation. As soon as you find something funny going on that you don't get it, put your hands up and ask so that we can clarify it. Okay, so let's carry on with this game now. So that's half. I'll just keep this half here for the time being. I'll bring it into the bracket at some stage. So that's AK plus BK e to the IKX. That's the blue, the green ones. Plus AK. Oh, where's the 2I? These ones should have a I here. You agree? I took out the 2 into the front here. But there should be an I there. So 1 over I. This one, so this should have been AK minus BK. Minus IBK. See this part here? It should be minus I. Because 1 over I is minus I. I clarified that above. So if I'm grouping these, it will be AK minus IBK. Those two parts here. Likewise, then it will become a plus BK, IBK. AK plus IBK. AK plus IBK. E to the minus IKX. Or just to make it into the shape that I want, let's rewrite that e to the minus IBK over 2 e to the IKX plus AK plus IBK over 2 e to the minus IKX. Nice thing is that there's no I in the denominator anymore. If I were to write this out, so this goes from k equals to 0 to infinity. If I take A naught, and k is naught, it'll be A naught over 2 minus I B naught over 2. Sorry, what happened there? Okay, and then on the other side, I'll have A naught over 2 plus I B naught over 2. Okay, we know B naught is 0. So this will be 0 anyway. Oh, they kill each other. Even if you didn't know they were 0, they kill each other. Plus, here we can get, now we've got to be careful how we write this. Let me write it like this. K equals to 1 to infinity. AK minus IBK over 2 e to the IKX plus sigma. I'm just breaking this up. K equals to 1 to infinity. AK plus IBK over 2 e to the minus IKX. Okay, now you've got to not blink and watch very carefully. Well, A naught over 2 plus A naught over 2 is just A naught. That part is easy. The second part, I'm also not going to do much. I'll write this as AK. Well, let me. Okay, let's just leave this as it is for now. All I want is A naught. Let me define something just to make this clearer for teaching purposes. Let's CK be AK minus IBK over 2. And if you look at C minus K, let me call this first guy here CK. I'm just giving him a new name, CK. So let's call the first guy AK minus IBK over 2. Let's now take C minus K, meaning that I must change K into minus K. So what will happen? It will become C minus K will be AK it will become AK plus IBK over 2. Why does it become plus? Because this I here, if you multiply that by I, you'll get I squared. Minus times minus is a plus. It's just a cosmetic way of writing it. For now, you can just say, well, I'm labeling it CK and C minus K. In other words, I'm calling it CK, I'm calling it CF minus K. But there's a reason why this is chosen. It's because of what I just said. If you multiply this minus I here by I, it becomes minus I squared, which is plus 1. So these are linked. But don't worry if you don't realize they're not linked yet. I'm just saying let's call this guy CF minus K. I shall now show you that they will all live happily ever after. Okay, let me keep that slide available there. So now I can say f of x. It's a bit of a long derivation, but we have to do it. Of course, a naught will be c naught. So this will be c naught plus sigma k equals to 1 to infinity. The first one is ck e to the ikx. The second one will be sigma c minus k e to the minus ikx. K equals to 1 to infinity. Now you can see the purpose behind this. So this can become C naught plus sigma ck e to the ikx. K equals to 1 to infinity. Here comes the trick. This is the part where I invoke a trick. What happens if I reverse the interval? If you have A to B, you make it B to A. How do you adjust that? In other words, if I change K to negative K, I can go backwards. I can then go from K equals to negative infinity up to negative 1, in which K has become minus K. In other words, I'm doing it backwards. So then I'll get to ck e to the ikx. Oh, now you see that the resemblances are here, except that this guy goes from 1 to infinity. This guy goes from minus infinity to 1, minus 1. Remember, we're only talking about whole numbers. Okay? And then we also have 0. He's here. So, if you take a number line, there's 0 there. So you're going from minus infinity, you're coming all the way to 1. Right? Well, whole numbers. And then from positive infinity to 1. So you can see every number is covered in that formula. In fact, I can now combine the entire game into this here. ck e to the ikx from k equals to negative infinity up to positive infinity into one nice compact formula, f of x. And this is the complex Fourier series. Neat, eh? So, unlike the cosine and sine, there are no two things to work out. AK and BK. Now there's just one thing, CK to work out. And another big shift in the game is that we are now going into the negative regime. The previous game was k equals to naught to infinity, cosine and cosine. Now we're covering minus infinity, plus infinity. We're covering the entire spectrum of numbers, whole numbers. Any questions? You see the mathematical gymnastics that we can do to actually bring it into the form that we want. Yes? You know, I lost. Yes? Yeah, yeah. Oh, because, so, are you okay from here to here and here to here?
Yeah.
The only move was to change, switch these things here. Then I said that I can compact this entire thing into one thing. So this thing goes from 1 to infinity, 1 to infinity. By me reversing this, I went from minus infinity to minus 1. So the only missing number is a naught. And that is covered because we do have c k equals naught. It's covered there. So I have covered all the numbers from minus infinity to plus infinity. Now, let us take c naught by itself in this formula here. When you put k equals to naught here, you get c naught e to the power naught. This k is naught. What's e to the power naught? 1. So that's c naught by itself. That's how it's integration. Any other questions? Well, we are not fully done yet. We now have to finish the last part, and that is to find the Fourier coefficients. So we can do exactly the same as we've done for the Fourier series with inner products and stuff. I'm not going to go through the entire details. We can just take the results. This CK, let me just write the result for you. Oh, hang on, think of an example here. What did I write the K for? Should I derive this? Oh, anyway, okay. Wait, let me derive it then. CK was AK minus I BK over 2. Okay. So that's like half AK minus I BK. And that's half. What was AK? Wasn't it 1 over 2 pi? Well, let's first deal with the 1 over 2 pi is for A naught. Let's deal with the most general form. 1 over pi integral. Let's leave the limits out now because either naught to 2 pi or minus pi to pi. If you want, we can just put minus pi to pi just to finish the problem. But AK was f cos kx dx minus I. BK was 1 over pi integral f sine kx dx. Yes, what do I want to achieve with this? Okay, yes. That's half, or 1 over 2 pi, you could say. Let's pull that out completely. Integral minus pi plus pi. And you can get f into what's left? Cos kx minus I sine kx. So this is an explicit derivation. I was trying to not do this, but I've done it. 1 over 2 pi integral minus pi to plus pi f. The limits are the same here, so I can bring all into one integral. The limits are minus pi plus pi in both. So there's nothing illegal in combining them. So you get f is a common factor, you get cos kx minus I sine kx. Now what's another way to write cos kx minus I sine kx? E to the minus I kx, not plus. E to the minus I kx dx. So that's the Fourier coefficient, CK. And it covers all possible cases. For all k. Even naught. In the previous work, only A naught had a 1 over 2 pi. But in this complex game, CK is 1 over 2 pi for all possible cases. That's the difference. In case you're wondering, how come that's the case? Well, it's like the sine and cosine were half each, and you put them together, and now it becomes 1. Combining cos and sine, really. Right, so now we know how to do this. I've now derived it. Oh, what about for change of interval? Let me just write this down and I'll give you a short break. change of interval. Then we will replace kx by k pi x over L. So we can get ck. F of x will be sigma ck e to the I k pi x over L. K equals to negative infinity up to plus infinity, where the coefficient ck is 1 over 2 pi or 1 over 2L from minus L to L, f of x e to the minus I k pi x over L dx. So the ck is not e to the minus here. And in the original formula, you have e to the plus I k x over L. It's quite a complicated formula, because if you plug this here into that, it looks like quite a hectic formula. Sigma 1 over 2L e to the minus L to L, e to the minus k pi x over L, brackets times e to the I k pi x over L. That's how you write it from A series. It's quite a formidable thing. But I hope now, by this time, you've understood how the game works. Let's take a short break at this point, and then after 5 minutes, we shall resume. You can just stretch your legs out.